Dr. Marcus Chen stands at the podium of the American Astronomical Society's winter meeting in New Orleans, January 2025. Behind him, a massive screen displays what looks like a ghost, a spectral image of our galaxy that seems both familiar and utterly alien. Before I show you what NASA has discovered, he begins with a slight smile. Let me start with a confession. For my entire career, I've been studying the Milky Way. 23 years of observations, calculations, and theories. And it turns out, I've been looking at only 5% of it. The audience murmurs. Chen clicks his remote. You know the old joke about the drunk man looking for his keys under the streetlight? Someone asks if that's where he dropped them. No, he says, but the light is better here. Well, fellow astronomers, we've all been that drunk man. We've been studying the Milky Way where the light is better, in the optical spectrum. Today, I'm going to show you what we've been missing in the dark. The image behind him transforms. The familiar spiral arms vanish, replaced by towering columns of gamma rays, vast bubbles of X-ray emission, and serpentine filaments of radio waves that stretch across tens of thousands of light years. The Milky Way everyone knows is gone, replaced by something that looks more like a cosmic storm than a serene spiral. Ladies and gentlemen, Chen announces, meet the invisible Milky Way. 95% of our galaxy has been hiding from us, not in distance, but in wavelength our eyes cannot see. Using data from the James Webb Space Telescope, Chandra X-ray Observatory, the Very Large Array, Fermi Gamma Ray Space Telescope, and over a dozen other instruments, we finally assembled the first complete electromagnetic portrait of our galactic home. And I promise you, it's nothing like what we expected. The room falls silent. On the screen, the invisible galaxy pulses with violent energy, streams with hidden matter, and glows with the light of processes that challenge our understanding of physics itself. What you're looking at, Chen continues, is not just a pretty picture. It's a revolution in our understanding of where we live. The invisible Milky Way isn't just hiding stars and gas. It's hiding answers to why we exist, threats we never knew about, and mysteries that will take generations to solve. So let's turn off the streetlight and see what's really out there in the dark. For all of human history, we've been trapped by our biology. Our eyes evolved to see a narrow slice of the electromagnetic spectrum, what we call visible light, running from red through orange, yellow, green, blue, indigo, to violet. This range, from wavelengths of about 380 to 700 nanometers, is all we can perceive naturally. It's like trying to understand a symphony by listening to only 3 notes out of an entire orchestra. Dr. Sarah Johansson at the Max Planck Institute for Astronomy has spent her career studying this limitation. Imagine you're an alien visiting Earth, she explains, and you can only see in radio waves. You'd completely miss the sun. It's dim in radio. You'd miss the stars, the blue sky, the green forests. You'd see a completely different planet. That's our situation with the Milky Way. We've been seeing only what glows in visible light, missing the vast majority of what's actually there. The problem is compounded by our location. We sit inside the Milky Way's disk, about 26,000 light-years from the galactic center, embedded in the Orion arm between the Perseus and Sagittarius spiral arms. Trying to map our galaxy from this position is like trying to map Manhattan while standing in a subway tunnel. You might see some nearby stations, guess at the layout from rumbling trains above, but most of the city remains hidden. Making matters worse is dust. The space between stars isn't empty, but filled with microscopic particles of carbon, silicon, iron, and other elements. These dust grains, typically less than a micrometer across, are incredibly effective at absorbing and scattering visible light. Looking toward the galactic center through optical telescopes is like trying to peer through a sandstorm that's 26,000 light-years thick. Dr. Edward Gibson at the University of Cambridge puts it in perspective. If the galaxy's dust suddenly vanished, the night sky would be transformed. the galactic center would blaze with the combined light of billions of stars, bright enough to read by. The spiral arms would be visible to the naked eye, stretching across the heavens. We'd see our cosmic home as it really is, not the dim, dust-obscured version we're familiar with. But dust is only part of the problem. Many cosmic phenomena simply don't emit visible light at all. Black holes, by definition, trap light. Cold gas clouds are invisible. Magnetic fields leave no optical signature. Dark matter, which makes up 85% of the galaxy's mass, emits nothing our eyes can detect. Even ordinary matter, when it's too hot or too cold, shifts its emissions outside the visible range. The journey to see the invisible began with radio astronomy in the 1930s. Carl Jansky, working for Bell Telephone Laboratories, discovered radio waves coming from the constellation Sagittarius, the direction of the galactic center. This was our first glimpse of the invisible galaxy, though few understood its significance at the time. The space age brought new revelations. Satellites carrying X-ray detectors in the 1960s discovered that the galaxy was filled with high-energy phenomena invisible from the ground. Infrared telescopes in the 1980s pierced through dust clouds to reveal hidden stars. Gamma-ray observatories in the 1990s showed us matter-antimatter annihilations and cosmic ray collisions. But these were isolated glimpses, like looking at an elephant through different keyholes and trying to imagine the whole animal. Each wavelength revealed part of the truth, but not the complete picture. It's only now, in 2025, that we have both the technology and the computational power to combine all these views into a single, coherent image. The revelation came from what NASA calls the Galactic Origins and Structure Survey, GOSS, a coordinated observation campaign involving space telescopes, ground-based observatories, and supercomputers. For 18 months, instruments observed the same regions of the galaxy simultaneously across the entire electromagnetic spectrum. The data volume was staggering, over 400 petabytes, equivalent to 80 billion DVDs. Dr. Chen, who leads the GOSS project, describes the challenge. We weren't just collecting data, we were trying to align observations taken by different instruments, at different times, with different resolutions, in different wavelengths. It's like trying to combine a photograph, an X-ray, a thermal image, and a radar scan into a single picture. Every pixel had to be precisely calibrated and cross-referenced. The computational challenge was equally daunting. The National Science Foundation's newest supercomputer, capable of 2 exaflops, 2 quintillion calculations per second, ran for 6 months solid to process the data. Machine learning algorithms had to be trained to recognize patterns across wavelengths, identify structures that appeared different in each spectrum, and reconcile conflicting observations. But when the final image emerged, it was worth every effort. The invisible Milky Way was revealed in all its hidden glory, a galaxy far more complex, dynamic, and violent than anyone had imagined. When the James Webb Space Telescope turned its golden hexagonal mirrors toward the galactic center in March 2024, astronomers expected to see through the dust and count stars. They got far more than they bargained for. JWST's infrared eyes revealed a hidden universe of stellar nurseries, failed stars, and structures that shouldn't exist according to our theories. Infrared light, with wavelengths longer than visible light but shorter than radio waves, has a special property. It can penetrate dust that blocks optical light. It's like the difference between fog and X-rays. Fog blocks visible light, but X-rays pass right through. Similarly, cosmic dust that creates dark lanes in optical images becomes transparent in infrared. Dr. Rebecca Martinez at the Space Telescope Science Institute led the JWST Galactic Survey. The first images made us question our instruments, she recalls. Where we expected to see a chaotic jumble of old stars near the galactic center, we found organized structures, filaments, shells, bubbles, and streams all arranged in patterns we'd never seen before. The galactic center, completely obscured in visible light, blazed in infrared like a cosmic Times Square. But it wasn't just the brightness that surprised astronomers. it was the diversity. JWST revealed at least 6 distinct types of objects that are invisible in optical light. Protostellar cores. These are stars in the earliest stages of formation, still gathering mass from surrounding gas. They glow only from the heat of gravitational compression, not nuclear fusion. JWST found thousands of them, 10 times more than models predicted. Each one is a future star, currently invisible to optical telescopes, that will one day light up the galaxy.
Brown dwarf populations. These failed stars are too small to sustain hydrogen fusion, but glow faintly in infrared from residual heat. JWST revealed that brown dwarfs outnumber regular stars near the galactic center by 3 to 1. They contribute significant mass to the galaxy, but almost no visible light. A dark population we've been missing in our census. Stellar cocoons. Massive stars still wrapped in their birth clouds of gas and dust. These cocoons block optical light, but glow brilliantly in infrared. JWST showed that star formation near the galactic center isn't suppressed as we thought, but hidden. The galaxy's core is an active stellar nursery, birthing giants that will eventually blow away their dusty veils. Infrared dark clouds. Paradoxically, some clouds are so dense and cold they appear dark even in infrared, silhouetted against the glowing background. These are the galaxy's stellar wombs, where the next generation of stars will form. JWST mapped over 10,000 such clouds, each a future star cluster waiting to be born. Hot dust streams. Rivers of warm dust flowing between star-forming regions, heated to hundreds of degrees by stellar radiation. These streams trace the movement of material through the galaxy, showing how gas and dust circulate like blood through cosmic veins. Hypervelocity stars. Stars moving so fast they'll eventually escape the galaxy entirely. In infrared, JWST could track their motion through dusty regions where they're invisible optically. Over 1,000 such stars were discovered, each one evidence of violent gravitational encounters near the galaxy's central black hole. But the most stunning discovery was the architecture of the galactic center itself. Instead of chaos, JWST revealed order. The central molecular zone, a ring of molecular gas surrounding the galactic center, showed elaborate structure. Vertical filaments rise thousands of light-years above and below the galactic plane like towers. These filaments, invisible in optical light, glow in infrared emission from warm dust and molecules. Dr. Adam Ginsberg at the University of Florida, who studies these filaments, was astounded. They're like cosmic skyscrapers, but made of gas and dust. Some are 150 light-years tall, but only a light-year wide. The physics required to maintain such structures challenges our understanding. They should collapse under their own gravity or be torn apart by tidal forces, yet they persist. JWST also revealed the true nature of the brick, a massive molecular cloud near the galactic center that puzzled astronomers for decades. In infrared, the brick showed internal structure, dense knots where stars are trying to form but can't, surrounded by shells of warmer gas heated by cosmic rays. It's a frustrated stellar nursery, where extreme conditions prevent normal star formation. The infrared view also solved a long-standing mystery about the galaxy's spiral arms. In visible light, the arms appear broken and fragmentary. In infrared, they're continuous and well-defined. The dust that obscures them optically glows in infrared, revealing the true spiral structure. Our galaxy has 4 major spiral arms, not the 2 we thought, with numerous smaller spurs including the Orion spur where Earth resides. Perhaps most remarkably, JWST discovered vast bubble structures throughout the galactic disk, some spanning thousands of light-years. These bubbles, blown by stellar winds and supernovae, are invisible optically, but glow in infrared from heated dust along their edges. They're like frozen explosions, preserving the record of stellar death and rebirth. Dr. Martinez summarizes the infrared revelations. JWST has shown us that the galaxy we thought we knew, old, stable, slowly evolving, is actually young, dynamic, and constantly recreating itself. Star formation isn't declining as we believed, but hidden behind veils of dust. The galaxy is more alive than we ever imagined. If infrared reveals the hidden architecture of our galaxy, X-rays expose its violent temper. The Chandra X-ray Observatory, after 25 years of operation and recent upgrades, has mapped our galaxy's high-energy phenomena with unprecedented detail. The X-ray Milky Way is a battlefield where stellar death, black hole feeding, and magnetic reconnection create temperatures of millions of degrees. Dr. Konstantin Petrov at the Harvard-Smithsonian Center for Astrophysics leads the Chandra Galactic Survey. In X-rays, he explains, we see the galaxy's temper tantrums. Every point of light is something violent, a stellar collision, a supernova remnant, an accretion disk around a black hole, or gas heated to temperatures that would vaporize any known material. The X-ray galaxy is surprisingly structured. Instead of random points of violence, Chandra revealed organized networks of hot gas, channels of high-energy particles, and patterns that suggest the galaxy has a circulatory system for extreme physics. The most dramatic discovery was the full extent of the Fermi bubbles. First detected in gamma rays in 2010, these massive structures extend 25,000 light-years above and below the galactic center. In X-rays, Chandra revealed their internal structure, not uniform bubbles, but complex networks of shock waves, hot gas filaments, and magnetic field lines twisted into helical patterns. Dr. Yang Liu at the University of Michigan studies these bubbles. They're like the galaxy's lungs, breathing hot gas in and out of the galactic disk. The X-ray observations show gas at 10 million degrees being channeled through magnetic tubes, rising from the galactic center like smoke from a cosmic chimney. The bubbles aren't static. Chandra detected waves propagating through them at thousands of kilometers per second, shock waves from ongoing energy injection at the galactic center. Something is still inflating these bubbles, pumping energy equivalent to 100,000 supernovae into them. Near the galactic center, X-rays revealed a disturbing truth. Our supermassive black hole, Sagittarius A star, is not as quiet as we thought. While it's not actively feeding now, X-ray echoes bouncing off nearby gas clouds show it was 1,000,000 times brighter just 200 years ago. These echoes, called light echoes, are like cosmic forensics, revealing past violence from reflections. Dr. Petrov describes the phenomenon. Imagine shouting in a canyon and hearing echoes. Now imagine the shout was a massive X-ray outburst from our black hole, and the canyon walls are gas clouds hundreds of light years away. We're hearing, or rather seeing, echoes of the black hole's last meal. The X-ray observations revealed dozens of previously unknown stellar mass black holes throughout the galaxy. These invisible objects reveal themselves when they feed on companion stars, heating the infalling gas to millions of degrees. Chandra found over 500 such X-ray binary systems, 10 times more than previously known. But perhaps the most surprising discovery was the X-ray web, a network of hot gas filaments connecting different regions of the galaxy. These filaments, typically at temperatures of 1 to 2 million degrees, are too hot to emit visible light and too cool to be easily detected until now. They form a cosmic network through which energy and matter flow. Dr. Marina Volkov at the European Space Agency, analysing combined Chandra and XMMM Newton data, made a startling connection. The X-ray web isn't random. It follows the galaxy's magnetic field lines. We're seeing magnetized plasma flowing along invisible highways, carrying energy from sites of stellar death to regions of stellar birth. It's the galaxy's power grid made visible. The X-ray view also revealed the true danger of our cosmic neighborhood. The galaxy experiences regular X-ray storms, periods when multiple supernovae and stellar collisions create waves of X-ray radiation that sweep through the galactic disk. Earth has been lucky, sitting in a relatively quiet bubble blown by ancient supernovae. But the X-ray data shows we're approaching the edge of this bubble. In about 10 million years, our solar system will leave this protected zone and enter a region of higher X-ray flux. While not immediately catastrophic, the increased radiation could affect Earth's upper atmosphere and potentially trigger climate changes. The galactic center in X-rays is particularly violent. Gas falling toward the central black hole doesn't fall smoothly, but in chaotic streams that collide,
creating X-ray flashes. These collisions happen constantly, making the galactic center flicker like a cosmic strobe light in X-rays. Dr. Petrov notes a sobering reality. If Earth were located within 3,000 light-years of the galactic center, life as we know it couldn't exist. The X-ray radiation would strip our atmosphere, the stellar density would destabilize our orbit, and regular supernova blasts would sterilize the surface. Our position in the galaxy's suburbs isn't just convenient, it's essential for our existence.
The radio sky tells yet another story of our galaxy, one written in magnetic fields and cold hydrogen, in pulsar beams and synchrotron radiation. The Very Large Array in New Mexico, combined with the ALMA Observatory in Chile and the Meerkat Array in South Africa, has created the most detailed radio map of the Milky Way ever assembled. This map reveals the galaxy's invisible skeleton, structures that hold it together, and channels through which energy flows. Dr. Naomi Watanabe at the National Radio Astronomy Observatory coordinates the Global Radio Survey. Radio waves show us the galaxy's infrastructure, she explains. If X-rays are the violence and infrared is the nursery, radio waves are the highways and power lines, the systems that connect everything. The first revelation was the true extent of the galaxy's magnetic field. While we knew the Milky Way was magnetized, radio observations revealed a magnetic structure far more complex and powerful than imagined. The field isn't uniform, but organized into spiral patterns that follow the galaxy's arms, with vertical components creating magnetic towers extending into the galactic halo. The magnetic field strength averages about 6 microgauss, 1,000,000 times weaker than Earth's magnetic field. But extended over the galaxy's vast volume, it contains enormous energy, equivalent to the combined output of 1 billion suns over 1,000,000 years. Dr. Brian Gainsler at the University of Toronto, a leading expert on cosmic magnetism, was amazed by the radio observations. We found magnetic tunnels, regions where field lines form tube-like structures that could channel cosmic rays and gas across thousands of light years. It's like discovering the galaxy has a subway system we never knew existed. These magnetic tunnels appear to connect star-forming regions with areas of stellar death, creating a recycling system for gas and energy. Material from dying stars flows along these magnetic highways to regions where new stars are born, maintaining the galaxy's cycle of stellar regeneration. The radio observations also revealed the galaxy's population of pulsars, rapidly rotating neutron stars that emit radio beams like cosmic lighthouses. The survey detected over 3,000 new pulsars, doubling the known population. Each pulsar is a physics laboratory, with magnetic fields 1 trillion times stronger than Earth's, and densities exceeding that of atomic nuclei. Dr. Victoria Caspi at McGill University studies these objects. Pulsars are the galaxy's precision clocks. By timing their pulses, we can detect gravitational waves, test Einstein's relativity, and map the distribution of matter in the galaxy. The new population revealed by radio surveys gives us thousands more tools to probe fundamental physics. But the most spectacular radio discovery was the full extent of the galactic center's filament population. Hundreds of filaments, each up to 150 light-years long but only a few light-years wide, rise perpendicular to the galactic plane. In radio waves, they glow from synchrotron radiation, electrons spiraling around magnetic field lines at near light speed. These filaments come in 2 varieties: thermal filaments glowing from hot gas, and non-thermal filaments glowing from relativistic particles. The non-thermal filaments are perfectly straight, defying gravity and stellar winds that should distort them. Their origin remains one of the galaxy's greatest mysteries. Dr. Farhad Yousefzadeh at Northwestern University, who discovered the first filaments decades ago, is still puzzled. They shouldn't exist. The energy required to maintain them is enormous. The magnetic fields needed to confine them are at the limit of what's theoretically possible, and they show no signs of decay despite being millions of years old. They're telling us something fundamental about the galaxy that we don't understand. Radio observations also revealed ghost arms, spiral density waves visible only in radio emission from hydrogen gas. These arms are offset from the optical spiral arms, representing the actual gravitational pattern that organizes the galaxy. Stars and gas clouds orbit through these density waves, getting compressed as they enter and triggering star formation. The radio sky also unveiled vast loops and shells of emission surrounding the entire galaxy. The largest, called the North Polar Spur, arcs across a huge portion of the sky. Once thought to be a distant structure, radio parallax measurements revealed it's only 500 light-years away, a nearby supernova remnant that's been expanding for 100,000 years. Dr. Jennifer West at the University of Toronto made a remarkable discovery about these structures. The loops and spurs aren't random. They form a coherent pattern, like we're inside a giant magnetic bubble. The solar system sits at the center of this bubble, protected by magnetic fields from cosmic rays and interstellar gas. It's like living inside a cosmic cocoon. The radio observations revealed one more surprise. The galaxy hums. There's a background radio emission that permeates the entire galaxy, pulsing with a 26 million year period. This cosmic heartbeat might be related to the sun's oscillation above and below the galactic plane, or it might be something more fundamental, the galaxy breathing as it rotates. At the highest energies, the Fermi Gamma Ray Space Telescope reveals a Milky Way that's essentially radioactive. Gamma rays, with energies millions to billions of times greater than visible light, show us the galaxy's most extreme phenomena: matter meeting antimatter, cosmic rays colliding at near light speed, and possibly even dark matter revealing itself through annihilation. Dr. Julie McEnery at NASA's Goddard Space Flight Center leads the Fermi science team. In gamma rays, the galaxy looks like a war zone. Every photon we detect represents something catastrophic: particles accelerated to energies we can't achieve on Earth, matter being converted directly to energy, or physics at the edge of our understanding. The gamma-ray sky is dominated by two features: the galactic plane glowing from cosmic ray collisions, and the mysterious Fermi bubbles extending far above and below the disk. But the detailed observations revealed far more structure than anyone expected. The galactic center excess remains one of astronomy's most tantalizing mysteries. There's more gamma-ray emission from the central region than can be explained by known sources. The excess has a very specific energy spectrum peaked at 1 to 3 giga-electron volts, exactly what many models predict for dark matter particle annihilation. Dr. Dan Hooper at Fermilab has championed the dark matter interpretation. If dark matter particles are their own antiparticles, they would annihilate when they meet, producing gamma rays. The galactic center, where dark matter density is highest, would glow in gamma rays exactly as we observe. We might be seeing dark matter for the first time, but alternative explanations exist. Dr. Tracy Slatier at MIT proposes a population of millisecond pulsars, rapidly spinning neutron stars too faint to detect individually, but collectively producing the observed gamma rays. The debate isn't settled, she notes, but either explanation is revolutionary. Either we're detecting dark matter or discovering thousands of hidden pulsars. The Fermi bubbles themselves have revealed unexpected complexity. Rather than uniform structures, they show internal features, jets, shocks, and regions of different intensity. The bubbles are still being inflated, with energy injection at their base equivalent to 100,000 supernovae. Dr. Dmitry Malyshev at the University of Erlangen-Nuremberg discovered that the bubbles have a sharp edge. The transition from inside to outside the bubbles happens over less than 100 light-years, incredibly sharp for structures 50,000 light-years tall. Something is confining them, creating a boundary that cosmic rays can't cross. It might be magnetic fields, or it might be physics we don't understand. Gamma-ray observations revealed the galaxy's cosmic ray accelerators. Supernova remnants, pulsar wind nebulae, and stellar clusters all contribute, but surprisingly, they can't account for all the cosmic rays we observe. There's a missing source producing about half the galaxy's high-energy particles. The most extreme discovery was the detection of pevatrons, cosmic accelerators capable of pushing particles to peta-electron-volt energies, 1,000 times higher than the Large Hadron Collider. Only a handful of these extreme accelerators exist in our galaxy, and their nature remains mysterious.
Dr. Felix Aharonian at the Dublin Institute for Advanced Studies studies these objects. Pervatrons represent physics at the absolute limit. The magnetic fields and shock waves required to accelerate particles to these energies shouldn't be possible according to standard models. Yet there they are, defying our theories.
The gamma-ray sky also pulses. Fermi detected regular variations in the gamma-ray background with multiple periods, 11 years matching the solar cycle, 2.2 years possibly related to cosmic ray propagation, and a mysterious 0.5-year period with no known cause. Perhaps most intriguingly, gamma rays revealed antimatter fountains at the galactic center. Positrons, anti-electrons, are produced at a rate of 10 to the 43rd per second, creating a vast antimatter cloud when they annihilate with normal matter. The source of this antimatter remains unknown. It's far more than supernovae and black holes can produce. Dr. William Gillard at the University of Oxford studies this antimatter mystery. Something at the galactic center is converting energy into matter-antimatter pairs on a massive scale. It might be dark matter annihilation, exotic physics near the black hole, or processes we haven't imagined. Whatever it is, it's producing more antimatter than exists anywhere else in the known universe. When NASA's supercomputers finally combined all the wavelength observations into a single, unified model of the Milky Way, the result was so unexpected that astronomers initially thought there was an error. The galaxy revealed by the full electromagnetic spectrum bore little resemblance to the serene spiral we thought we knew. Dr. Marcus Chen, standing before the first complete multi-wavelength map, felt like early explorers must have felt seeing accurate maps after years of guesswork. It was humbling and exhilarating. We thought we understood our cosmic home, but we were like blind people touching different parts of an elephant. Only when we combined all the observations did we see the true beast. The unified view revealed that our galaxy is not one structure but many, superimposed and interacting. The visible galaxy. The familiar spiral arms traced by bright stars and emission nebulae, what we've always called the Milky Way. This represents only about 5% of the galaxy's total electromagnetic output and less than 1% of its mass. The infrared galaxy, a hidden realm of dust structures, failed stars, and stellar nurseries. This infrared galaxy is actually brighter than the visible galaxy, radiating more total energy, but invisible to our eyes. The radio galaxy, a vast network of magnetic fields and cold gas, organized into structures that dwarf the visible spiral arms. The radio galaxy extends far beyond the visible disk, reaching 200,000 light-years into intergalactic space. The X-ray galaxy, a violent realm of million-degree gas, stellar explosions, and black hole feeding. The X-ray galaxy pulses and flares unpredictably, its energy output varying by factors of thousands over time. The gamma-ray galaxy, the extreme frontier where matter converts to energy, particles reach impossible energies, and perhaps dark matter annihilates. The gamma-ray galaxy is the smallest in extent but most energetic, producing photons billions of times more energetic than visible light. These aren't separate galaxies, but different aspects of the same galaxy, like different organs in a body. They interact in complex ways that we're only beginning to understand. The synthesis revealed several profound truths about our galaxy. First, the Milky Way is alive in ways we never imagined. It breathes, with gas flowing up from the disk and raining back down. It circulates, with magnetic channels carrying energy from sites of stellar death to regions of birth. It pulses, with waves of star formation triggered by spiral density waves. The galaxy is less like a static island of stars and more like a living organism. Second, the galaxy has memory. Events from millions of years ago, ancient supernovae, past feeding of the central black hole, collisions with dwarf galaxies, have left permanent scars visible in different wavelengths. The gamma-ray bubbles remember an eruption 10 million years ago. Radio loops preserve the record of stellar explosions from 100,000 years past. X-ray echoes reveal black hole feeding from mere centuries ago. Third, the galaxy is far more dangerous than we thought. The combined observations revealed that most of the galaxy would be lethal to life as we know it. Gamma-ray bursts, X-ray flares, cosmic ray bombardment, and magnetic storms make the majority of the galactic disk uninhabitable. Earth exists in a rare quiet zone, a cosmic Switzerland surrounded by violence. Dr. Aomawa Shields at UC Irvine, who studies habitability, was sobered by the findings. The galactic habitable zone is much smaller than we thought. Maybe only 10% of stars are in regions calm enough for life to evolve. We're not just lucky to be on Earth, we're lucky to be where Earth is in the galaxy. Fourth, the galaxy is still evolving. Far from being a mature, stable system, the Milky Way is dynamic and changing. Star formation, once thought to be declining, is actually accelerating in hidden infrared merceries. The spiral arms are not fixed but constantly reforming. The central black hole, currently quiet, shows signs of awakening. Finally, and perhaps most remarkably, the synthesis revealed that we're missing something fundamental. Even accounting for all electromagnetic radiation, all known matter, and all detected phenomena, the numbers don't add up. The galaxy's gravitational behavior requires far more mass than we can see, even with our complete electromagnetic view. Dr. Chen explains the discrepancy. We can now see 100% of the electromagnetic spectrum, but we're still missing 85% of the galaxy's mass. Dark matter isn't just a theoretical construct, it's a massive, invisible presence shaping everything we can see. The invisible galaxy we've revealed is itself embedded in something even more invisible. The revelation of the invisible Milky Way doesn't just change our understanding of our own galaxy, it revolutionizes our view of how all galaxies evolve. If we've been missing 95% of our own galaxy, what have we been missing in our observations of distant galaxies? Dr. Roberto Gonzalez at the Carnegie Observatories leads efforts to apply these findings to cosmology. Every galaxy evolution model we've created has been based on visible light observations. Now we know that's like trying to understand human civilization by only looking at streetlights from space. We've been missing most of the story. The multi-wavelength Milky Way reveals that galaxies are far more complex systems than our models assumed. They're not just collections of stars with some gas and dust, but intricate machines with multiple interacting components. The infrared observations show that star formation doesn't decline smoothly with time, but occurs in waves and bursts, hidden behind dust veils. Many galaxies classified as dead or quenched might actually be forming stars vigorously in dust-shrouded regions invisible to optical surveys. The X-ray revelations suggest that galactic centers are far more active than believed. Black hole feeding, even at low levels, creates feedback that can regulate star formation across entire galaxies. The X-ray web connecting different regions means that events in one part of a galaxy can affect regions thousands of light years away. The radio discoveries imply that magnetic fields play a crucial role in galaxy evolution, channeling gas flows and confining cosmic rays. Galaxies might be more like electric circuits than gravitational wells, with currents of charged particles flowing along magnetic field lines. The gamma-ray findings hint at processes we don't understand: dark matter annihilation, extreme particle acceleration, antimatter production. These high-energy phenomena might be common in all galaxies, but completely invisible to traditional observations. Dr. Priya Natarajan at Yale University sees profound implications. We need to rebuild galaxy evolution theory from the ground up. The invisible processes might actually dominate galaxy evolution. Dark matter annihilation could be a major energy source. Magnetic fields might determine where stars form. Cosmic rays could drive galactic winds. Everything we thought we knew needs reconsidering. The findings also impact our search for life in the universe. If most of galaxies are hostile to life due to high-energy radiation invisible in optical observations, the number of potentially habitable planets might be far smaller than estimated. Conversely, the discovery of vast amounts of organic molecules in infrared dark clouds suggests that the building blocks of life are more abundant than thought. Every galaxy might be seeded with complex chemistry, ready to spark life in the right conditions. Dr. Dimitar Sasolov at Harvard considers the implications. The invisible galaxy shows us that the universe is simultaneously more dangerous and more fertile than we imagined. Life faces more challenges but has more resources. The question isn't whether life exists elsewhere, but whether it can survive long enough to evolve intelligence. Perhaps the most profound revelation from the multi-wavelength galaxy is not what we can see, but what we still cannot. Even with observations across the entire electromagnetic spectrum, 85% of the galaxy's mass remains invisible. This dark matter shapes everything we observe, but refuses to reveal itself directly. Dr. Catherine Fries at the University of Texas, a pioneer in dark matter research, sees the invisible galaxy as a crucial clue. The multi-wavelength observations have eliminated hiding places for normal matter. We've counted every star, mapped every gas cloud, detected every brown dwarf. The missing mass isn't hidden, it's truly dark, interacting only through gravity. The shape of this dark matter halo is revealed indirectly through its gravitational effects on visible matter. It extends far beyond the visible galaxy, reaching out 300,000 light-years or more. It's not uniformly distributed, but clumped, with dense streams and voids that channel the motion of stars and gas. The gamma-ray observations provide tantalizing hints that dark matter might not be completely dark. The excess emission from the galactic center has exactly the spectrum expected if dark matter particles annihilate each other. If confirmed, this would be the first detection of dark matter through anything other than gravity. Dr. Neil Weiner at New York University explains the possibility. Dark matter might glow, but in gamma rays, not visible light. If dark matter particles are their own antiparticles, what we call Majorana fermions, they would annihilate when they collide, converting their mass to energy. The galactic center, where dark matter is densest, would be the brightest source. But dark matter might not be the only invisible component. The multi-wavelength observations revealed regions where even electromagnetic radiation behaves strangely, zones where physics seems different. Near the galactic center, there are pockets where radiation doesn't propagate normally. X-rays that should travel in straight lines curve. Radio waves that should maintain constant frequency shift. Gamma rays disappear without being absorbed. These dark zones might be regions where space-time itself is modified by extreme gravity or exotic matter. Dr. Claudia de Ram at Imperial College London studies these anomalies. We might be seeing regions where general relativity breaks down, where quantum effects become important on macroscopic scales. These dark zones could be windows into quantum gravity, the theory that unifies quantum mechanics and general relativity. The synthesis of all wavelengths also revealed dark flows, streams of matter moving in ways that don't match the visible galaxy's gravity. Stars and gas clouds follow trajectories that require unseen masses channeling their motion. These might be dark matter streams, or they might be something else entirely. Dimensions beyond the three we perceive, creating gravitational effects from outside our normal space-time. The revelation of the invisible Milky Way is not an end, but a beginning. New technologies and missions planned for the next decade will reveal even more hidden aspects of our galaxy. The Square Kilometre Array, SKA, being built in Australia and South Africa, will increase radio sensitivity by a factor of 50. Dr. Philip Diamond, Director General of SKA, describes its capabilities. We'll be able to detect every pulsar in the galaxy, map every hydrogen atom, trace every magnetic field line. The invisible will become visible in exquisite detail. The Nancy Grace Roman Space Telescope, launching in 2027, will survey the entire galactic bulge in infrared with 100 times the speed of Hubble. It will discover every brown dwarf, map every dust cloud, and track the motion of millions of stars to create a 3D map of the galaxy's dark matter. The proposed Lynx X-ray Observatory would be 100 times more sensitive than Chandra, able to detect X-ray emission from normal stars throughout the galaxy. We would see the hot coronae of stars like our Sun, track stellar winds, and map the temperature of gas with unprecedented precision. LISA, the space-based gravitational wave detector, launching in the 2030s, will add an entirely new dimension to our observations. It will detect the gravitational waves from binary systems throughout the galaxy, revealing populations of black holes, neutron stars, and white dwarfs that emit no electromagnetic radiation at all. Dr. Kelly Holly Bockelman at Vanderbilt University anticipates LISA's impact. We'll go from seeing the galaxy to feeling it. Every binary system creates gravitational waves, ripples in space-time itself. LISA will reveal millions of invisible binaries, showing us the galaxy's hidden dance. Future neutrino telescopes will detect the ghost particles streaming from the center of stars and the edge of black holes. The proposed Pacific Ocean neutrino experiment would be sensitive enough to detect neutrinos from every supernova in the galaxy, providing warning days before the explosions become visible. But perhaps the most exciting development is in computational power and artificial intelligence. The next generation of supercomputers will be able to simulate the entire galaxy at the resolution of individual stars, comparing models with multi-wavelength observations to understand the physics we're missing. Dr. Rachel Somerville at the Flatiron Institute leads these simulation efforts. We're approaching the point where we can create a complete digital twin of the Milky Way, accurate down to individual star systems. By comparing simulations with observations across all wavelengths, we can identify what physics we're missing, what dark components must exist. Machine learning is already revolutionizing analysis. AI systems can identify patterns in multi-wavelength data that humans miss, finding connections between phenomena in different wavelengths that reveal underlying physics. As we stand at this moment of revelation, having finally seen the true face of our galaxy across all wavelengths of light, we must reckon with a transformed understanding of our place in the cosmos. We are not residents of the galaxy we thought we knew. The serene spiral of visible stars is merely the facade of a far grander, more complex, more violent structure. We live inside a cosmic maelstrom of invisible forces, protected by accidents of position and time that allowed life to emerge and evolve to the point where we could discover our true situation. Dr. Marcus Chen, reflecting on the complete revelation, offers a final thought. Every civilization has its moment when it truly sees its place in the universe. For humanity, that moment is now. We've finally seen our complete cosmic home, not just the pretty visible parts, but the whole, magnificent, terrible truth. We're smaller than we thought, luckier than we knew, and part of something far grander than we imagined. The invisible Milky Way teaches us humility. We spent centuries studying 5% of our galaxy and thought we understood it. How much else have we missed? How many other invisible realms await discovery? The universe we see is just the beginning of the universe that is. It teaches us connection. Every atom in our bodies has traveled through the invisible structures we've discovered, accelerated by magnetic fields we couldn't see, heated in X-ray plasmas we didn't know existed, processed through dark clouds we've only now revealed. We're not just in the galaxy, we're woven from its invisible threads. It teaches us gratitude. Earth's position in a quiet bubble, protected from the galaxy's violence, is extraordinarily fortunate. The invisible galaxy shows us a cosmos mostly hostile to life, making our existence even more precious. And it teaches us possibility. If we missed 95% of our own galaxy, what else might be hiding in plain sight? Dark matter, dark energy, dark dimensions. The invisible galaxy reminds us that nature's imagination exceeds our own. As we continue to develop new instruments and techniques, we'll undoubtedly discover even more invisible realms. The galaxy will continue to surprise us, challenge us, and expand our conception of what's possible. The story of the invisible Milky Way is ultimately the story of human curiosity and ingenuity. How we've learned to see beyond the narrow window of our biological senses, to perceive realms of light and energy that would otherwise remain forever hidden. It's a testament to our species' relentless drive to understand our cosmic context, no matter how challenging or humbling the truth might be. We now know that we live in a galaxy that's 95% invisible to our eyes, filled with violence and beauty in equal measure, shaped by dark forces we don't understand, and connected in ways we're only beginning to perceive. This knowledge doesn't diminish us, it elevates us, making us conscious participants in a cosmic drama far grander than our ancestors could have imagined. The invisible galaxy is no longer hidden. Through human ingenuity, determination, and wonder, we've pulled back the veil and seen our cosmic home as it truly is. And in seeing the galaxy completely, we see ourselves more clearly, tiny, temporary, but capable of perceiving and understanding wonders that dwarf us in every dimension. This is our gift and our burden, to be the part of the galaxy that can see itself, that can know itself, that can marvel at its own hidden beauty and terrible power. We are the universe's way of looking at itself, and through our instruments and equations, the invisible has become visible, the hidden has been revealed, and our cosmic home has finally shown us its true face. Thank you so much for joining me on this extraordinary journey through the invisible realms of our galaxy. When we started, I promised to show you the 95% of the Milky Way that's been hiding from us, and I hope you're as amazed as I am by what we've discovered. From infrared stellar nurseries to X-ray violence, from radiomagnetic highways to gamma-ray mysteries, our galaxy is far more complex and beautiful than we ever imagined. If this exploration has blown your mind like it has mine, please hit that subscribe button and ring the notification bell. We have so many more cosmic mysteries to explore together. I'd love to hear your thoughts in the comments. What surprised you most about the invisible galaxy? What other cosmic secrets would you like us to investigate? Remember, every time you look up at the night sky, you're seeing only 5% of what's really there. The other 95% is all around us, invisible but now known, hidden but now revealed. Until next time, keep looking up, keep wondering, and remember, the universe you see is just the beginning. Thank you, and stay curious.